Okay, so we're very happy to have Olivia Borghi from the University of Melbourne, who will talk about commutativity and higher algebraic objects.
Yeah, hi. I want to start by thanking the organizers and Martin for inviting me. It's a pleasure to be here virtually. The name of my talk is Commutativity in Higher Algebraic Objects. And when I say higher algebraic objects, I'm referring specifically to monoidal infinity categories and infinity operands. For the sake of the length of this talk, as well as accessibility, I'm going to be focusing on monoidal infinity categories. And the sort of goal of this talk is I want to get to a point where the audience has some understanding of what a G-monoidal infinity category is. And so I'm going to start by building all of the sort of one-dimensional analog stuff, and then we're going to work our way up slowly to infinity category land stuff. And just as a brief note, if I say infinity category, there are a ton of models for infinity categories. I'm referring to quasi-categories, basically, anytime I say that in this talk. So, okay, so we're going to start with one categories. So a symmetric monoidal category is an algebraic object in the category of categories. Specifically, it's a category in which if I have a couple of objects, I can have a tensor product of these things. Normally, we would define this sort of directly by saying it's a category equipped with this functor C cross C2C that we think of as the monoidal product, and that this functor needs to satisfy certain commutative diagrams. But I'm going to define it in a somewhat unfamiliar way in using operands. And it allows me to sort of define it in one sentence, but in order to do that, we have to build a bunch of machinery first. So I'm going to start by building an operand. It's called the parenthesized symmetry operand. So, oh, that's very thick. There we go. So that looks something like this. So if you're unfamiliar with operands, I don't know if anyone in the audience is unfamiliar with operands, but if you are, just imagine I'm building a sequence of groupoids. In this case, this operand is in the category of groupoids. So imagine I'm building a sequence of groupoids indexed by the natural numbers. And then a little later in the talk, I'll explain what makes this collection of groupoids into an operand. So PA sigma n is a groupoid. In order to explain what each of these is, I'm going to go into depth on PA sigma 4. Okay. So the objects of this category of this groupoid are what's called parenthesized permutations on 4 letters. So a given object in this looks something like this. I have, say, x1, x4, x2, x3. So I choose some permutation on 4 letters here, and then I choose some parenthesization of this. And you might want to think of the parenthesization as the order in which I'm multiplying things. So as an example, it could be something like this. Great. So if I have another object, maybe something that looks like this, x2, x1, x3, x4, with a different set of parentheses, then the morphisms in this groupoid are quite simple. So since it's a groupoid, they're all isomorphisms. And how this groupoid works is there's going to be a unique isomorphism between any 2 objects. So simple enough. Okay, so what makes this collection of groupoids into an operand is it has something called an operatic composition. I'm going to write that down, and then I'm going to draw some pictures to help us understand what's going on.
Sorry, the set of objects is all permutations equipped with this extra parenthesization.
Yeah, so for PA sigma 4, it has to be of length 4. for PA sigma n of length n or whatever. And then all of the morphisms are just, there's a unique one between any two objects. We're going to build some generic versions of this later that are a bit more complicated, but for the case of PA sigma, it's quite simple. Okay, so an operatic composition map looks something like this. And the idea here is I'm going to have some element of the nth groupoid here. And you want to think of that as having like n inputs. And then I'm plugging into it elements from other groupoids in our operad. And then that's giving me out a new element. And so if you want, we can look at this like they're trees. So if I have something like n equals 3, and we have something that looks like this, where it has 3 inputs and 1 output. And I could have, say, k1 equal to 3 as well. K2 equal to 1. And K3 equal to 2. Then the idea is I can plug each of those into the inputs of the original one and come out with a new element. In this case, it would be in 6, in the 6th groupoid. So that would look something like this. That's just 1, and then 1, 2. Okay. So in the case of PA sigma, how this works is I might have x1, x3. Let's just do x2. And then I said k1 is 3, so maybe I'll have x1, x2, x3 with these parentheses, x1, and then say x2, x1 for k3. So how the operatic composition works on these, can I move this? Yes, okay, that's better. So I'm going to take each of these and plug them into its corresponding slot. So I'm going to plug this into where x1 is here. So to begin with, it would look something like this. Just take that same element and put it where that x1 is. And then put parentheses around the whole thing. I have here x1. I'm going to plug that into where x2 is. So we won't do that quite yet. And then I have this one that's x2, x1, and I'm going to plug that into where x3 is. But I have to re-index accordingly. So now that this has gone all the way up to 3, x3, or I guess we should do x1 first. I'm going to plug x1 into here. But since we need to re-index, it's going to actually be x4. And then I'm going to plug x2 into here. And that one is going to be x6, x5. And we need to put parentheses around it accordingly, like this. And then since the isomorphisms between any two objects is just a unique one, we don't really need to pay attention to how that's working operatically. Okay. So that with that constructed, we can actually define a symmetric monoidal category. It's an algebra over this operad. If you're unfamiliar with algebras over operads, they come equipped with this sort of structure map that looks like this. PA sigma n cross C to the n. That's just the Cartesian product of categories in this case. And it goes down to just C here. And the way that this is giving us what we want is if we look at PA sigma 2, and specifically the element just x1, x2. And then I pick, say, two objects here, A, comma, B. This is going to map down to C, and it's going to point out a tensor B. So if you just take this element x1, x2 and PA sigma 2 and leave the category, the C part blank, then that defines our functor, our monoidal product functor. So similarly, I can have the object x2, x1 cross the same objects. And this is going to point out B tensor A. And then the unique isomorphism connecting these things along with the identity maps here is going to point out a commutativity isomorphism here. And so before, in the normal definition of a symmetric monoidal category, we have that commutative diagrams that it needs to satisfy. By defining it as an algebra over this operad, all of those things are just sort of carried over in the information of this algebra. So we get the definition of the monoidal functor, and it behaves exactly as we would like it to, all in one fell swoop, just by defining it as an algebra over this thing.
Can I ask, when you say an algebra, but C is assumed to already be a category?
Yes, C is an object. So I said it's a operad in the category of groupoids. You can think of it as an operad in the category of categories, in which it just happens to be that every object is a groupoid. And then the algebra is just another object in the category that it's in. So in this case, categories. And yeah. Okay, so if you're familiar with other sort of commutative monoidal categories, the one you've probably heard of is a braided monoidal category. And so using the same sort of machinery, we can define a braided monoidal category as well. What we would first need to do is construct another one of these operads like PA sigma, but now for braids. So we'll call it PAB. So the objects of PAB, say 4, are going to be identical to the objects of PA sigma. So if I just look at the same object, x1, x4, x2, x3 here. And then x2, x1, x3, x4. I should put that lower. The only difference now is in the isomorphisms of this groupoid. And instead of having a unique isomorphism connecting any two objects, I'm going to have an infinite number, actually. And the reason why is because each of these isomorphisms is going to correspond to a braid in the 4th braid group that sort of corroborates the underlying order of these things. So as an example, I would have to connect x1 to x1 like this, x2 to x2, perhaps like this, and then so on and so forth. So this is an example of a braid that connects these. And so there will be a corresponding isomorphism between these two objects, relating to that specific braid. So the braid groups have this nice property that each of them maps down to the corresponding symmetric group like this. And so if you want, we can think of this braid as an element of the 4th braid group, call it B, say. And then pi 4 of B is precisely the element of the symmetric group that sends 1, 4, 2, 3 to 2, 1, 3, 4. Like this. Okay. So so far we just have like a sequence of groupoids again, but we don't have a composition defined the way we had for the symmetric group. How the composition works for the parenthesized braid group is on the level of objects, it's identical to PA sigma, but on braids, we do something that's called cabling. So if I'm trying to, what's that?
I was just wondering, this groupoid, can I think of it as like the braid group acts on the set of parenthesized letters and it's the action groupoid?
Yeah. So I mean, like, the A braided monoidal category is a category that has the braid group acting on the iterated monoidal product. And so that's sort of what these operads are trying to encode, is just getting that action out. So yeah, you can definitely think of it that way. Yeah, okay, so cabling. If I have, say, this very simple braid here, and I want to plug into it, so this goes from x1, x2 to x2, x1, and I want to compose into it, say, this pure braid, and maybe this braid, where this is x1, x2, and this is x1, x2. Maybe this is x2, x1, and this is x1, x2. Then the idea here is I take a strand of my original braid and I replace it with the entire braid that I'm plugging into it. So I'm going to take this and replace that first strand with it. So I'll have something like this, x1, x2, this pure braid down like this. So then I have x1, x2 here. And then we would have x4, x3. Once again, on the level of objects, it works the same way as the parenthesized symmetry operad. And then this would go like this, where I have x3 and x4 here. Once again, parentheses like this. So I get out a whole new braid just by sort of treating the strands like they're an entire braid. This is our notion of operatic composition for the parenthesized braid operad. So then in algebra, over this operad is precisely a braided monoidal category. And the reason why is before we had this unique isomorphism that gave us a single commutativity isomorphism, but now we have one corresponding to just, one braid. But if you do that again, it gives you a new one entirely. And you can just keep doing this by twisting and twisting and twisting and twisting. And that's how a braided monoidal category works. So the goal here is we would like to just sort of find this pattern and make it in generics so that there might be all sorts of different notions of commutativity for these things. So the setup for the two examples I've given so far is that we have some sort of sequence of groups equipped with group homomorphisms like this. And they assemble into an operad in groupoids that looks something like this, so that we can define an algebra over them. So this sort of generic construction is what's called a parenthesized action operad. I'm not going to go into the exact definition of what an action operad is, because essentially what it is it's a sequence of groups with group homomorphisms down to the symmetric group that can form into an operad in this way. So each of them has a unique operatic composition. You can't define that generically. It's different for each one. But sort of heuristically, what you want is there to be some notion of a direct sum of these elements, and then like a block action of these things. So there's something called a block braid, where you treat a bunch of strands as a single strand and then do the braid action on that. And so you want something like that generically. And there are quite a few examples of these action operads. So I'm going to write some down here.
Is it right that if you just have a group homomorphism to sigma n, that's not enough data for an action operad?
It is not enough because you can't necessarily define an operad with that. You don't necessarily have a good operatic composition on those things. Yeah, does that sort of make sense?
Yeah.
So what's that?
No, sorry.
Okay. You're fine. So if I have G equal to sigma, we get out the algebras are symmetric monodal categories, as we saw. For the braid groups, we get out braided monodal. If I choose a sort of trivial action operad in which there are no isomorphisms between any two objects unless they are the same object, then what I get out is just a notion of a monoidal category that's not necessarily commutative at all. So this would just give me a monoidal category. There's a sequence of groups called the ribbon braid groups, which are just like the braid groups, but you can sort of twist a single strand on itself as if it were like a ribbon. The ribbon braid groups give out a notion of ribbon braided monoidal categories. And these constructions show up in TQFTs sometimes. And then my last example is the cactus groups. They give you a notion of something called a cactus monoidal category, but this is also sometimes referred to as a coboundary category. And coboundary categories show up in the representation theory of quantum groups. Specifically, there's something called the category of crystals associated to a quantum group, and it happens to have this cactus monoidal structure or coboundary structure. So yeah, with this definition, we can get new notions of commutative monoidal categories where the commutativity is governed in some sense by one of these sort of permutative groups. Okay.
Sorry, Olivia. I
Yeah.
have a question. If we think of the example of symmetric monoidal categories, and we compare with a maybe more classical definition that I would find on Wikipedia of a monoidal category with this monoidal structure and the associator and the left uniter and right uniter and the symmetry isomorphism satisfying a few equations, then it becomes a theorem, Maclean's coherence theorem and its symmetric version, that those are enough to guarantee that any other way of moving the parentheses around will give you the same isomorphism, right? But from this point of view that you're presenting, you bake that fact into the definition. You force with this unique isomorphism in the groupoid, you forced all of those different ways of moving the expressions around to give you the same isomorphism. So would you say that from that point of view, the theorem becomes that just picking out the monoidal structure and these few pieces of structures, associator and uniter and braiding, extend uniquely to one of those PA sigma algebra structures, right?
Yeah,
is that
totally.
And is there a generalization of that fact for those other choices of G? Is there always some kind of small set of just a few pieces of structure that extend uniquely to the whole? Like, is there some kind of generalized Maclean coherence theorem for those? Or?
So not in every case. In the cactus groups, there actually is somebody went through the trouble of like making the same sort of coherence theorem where they were like, all of that information is just these commutative diagrams. But I don't think it's necessarily the case for every action operad. So
I see. So each one of those would be a theorem in its own right. There's not just a general recipe to cook up generators and relations.
Yeah, at least I don't know. It might be possible to do that. Nobody's done it.
Okay.
But
thank you.
Yeah, I mean, it's the same sort of thing where like the composition of these operads is defined uniquely for each one. You can't do it generically. And so I think it's the same sort of problem.
Got it. Thank you.
But it's kind of cool that if you look at what these action operads are doing, you can sort of get these pictures associated to the commutative diagrams that you want satisfied. And you can draw those pictures and see that it works exactly as you would like it to.
Okay, so you have some toolkits to tackle that problem, at least.
Yeah, the one direction is easier. But yeah.
Okay, thank you.
Okay, yeah, so as the next step, I'm going to give yet another unfamiliar definition for a symmetric monoidal category. Stick with me here. I'm doing this for a reason. So first thing I'm going to do is I'm going to define a category. it's the skeleton of the category of finite pointed sets. I'm going to call it fin star. So the objects of this are finite ordinals like this. And then maps between objects are finite pointed set maps. So if I have something like this, I need the fixed point to go to the fixed point, but I can send anything to the fixed point, and otherwise it's just a set map. So it can be whatever. If I send something to the fixed point, you might want to think of it as like deleting it. But it looks something like this. This is the category of finite pointed sets.
What is n
Okay.
in this case?
What's that?
Which, like, say, what would be the object 2? What would it look like in your?
It would look like this.
I see.
Yeah. Okay, so now we're going to take a sort of brief foray into two-category theory, but I'm going to make it as painless as possible. We're only going to have two categories involved here. The first one is going to be this category of finite pointed sets, just thought of as a discrete two-category. So it's only has trivial 2 arrows, so not much to worry about. And then the other one is going to be the two category of categories. So if you've seen any two categories before, you've seen this one. Its objects are categories, its morphisms are functors, and its 2 arrows are natural transformations. So now I want to imagine we have what's called a pseudo-functor. So this is just like a map of 2 categories if you want. From the category of finite pointed sets to this 2 category of categories. I'm going to call it C for a reason. And I'm going to require only one thing to be true about this pseudo-functor. And it's a sort of like Siegel condition. Specifically, I want the image of n, so like C of n, to be isomorphic to the image of 1 to the n, where that's just the Cartesian product of categories. So we're going to call this a Siegel condition. And we'll say that this pseudo-functor is Siegel. Okay, so
and
now
the
if
isomorphism, sorry, is still given by the usual Siegel maps from left to right, right? Whose different
What do you mean?
component. Well, it's not just a random isomorphism between those.
No,
right?
no,
So
it is a specific one.
Yeah, it's the usual one. Yeah, okay, that's discarding all elements except 1, and you do that in each coordinate. Yeah, okay, thank you.
Yeah, sorry, I'm kind of brushing over that. But yes, it is like a very specific isomorphism. Yeah, anyways, so if we imagine there's this commutative diagram in FinStar that looks like this. And I'll explain what each of these maps is in a second. Sigma is the map from 2 to 2 that swaps 1 and 2 and sends the fixed point to itself. And mu is the map from 2 to 1 that just sends 1 and 2 to 1. So the composition of these maps is just mu itself. So this is a commutative diagram because the swapping it and then sending them both to 1, it doesn't change anything about the character of that set map, right? So since this is a pseudo-functor and it has this Siegel property, the image of this in the category of categories, in the 2 category of categories, is going to look something like this, where I have the image of 2 to the image of 2, where this is a sort of swap map. It's going to go down to the image of 1. And mu is we're going to think of as our monoidal product. So since this is a pseudo-functor, and what makes it a pseudo-functor as opposed to just a functor is that it doesn't respect composition on the nose, but rather up to, in this case, a natural transformation. And so we're going to have this commutative diagram that's only commutative up to a 2 arrow. And so this is actually giving us all of the information that we were looking for in a symmetric monoidal category. It gives us our monoidal product via the image of mu. It gives us a commutativity isomorphism via this commutative diagram that I've drawn on the right here. And all of the coherency information is contained in fin star. So once again, we can kind of do that all in one fell swoop. So we could just stop there and say that this is a definition for a symmetric monoidal category. It's a pseudo functor that is Siegel from the category of finite pointed sets to the category of categories. But instead, we're going to do something
Olivia?
a little strange. Yeah.
Just to clarify, do you want that 2-cell to be invertible, or you allow any natural transformation there?
It is, in this case, invertible.
Okay.
Yes.
Thanks.
Yes. Yeah. It's a natural isomorphism in this case.
Thank you.
Yeah. Okay. So rather than just like leaving that as the definition, I'm going to use something called the Grothendieck construction to sort of redefine this or repackage this. So the category of pseudofunctors from fin star to cat that are Siegel turns out to be equivalent to the category of what's called op fibrations. Op fibrations over C. Or no, I'm sorry, over fin star. And that are Siegel in a different sense that I'll explain in a second. The Grothendieck construction tells us that this equivalence exists. And it would look something like this. What it means for this to be Siegel now is that the fiber over n is equivalent to the fiber over 1 to the n. And again, as Martin noted, this is a very specific equivalence. It's induced by a specific map, but I'm kind of going to brush over that. So then this is the definition we're going to use. We're going to say...
Did you say what the map is?
This map? So CO times is a very specific category called the category of operators associated to a symmetric monoidal category. And so it's kind of... its objects are lists of objects in C. And then its morphisms are, it's kind of hard to explain. I'm deliberately brushing it over because I think it's easier to understand it from this perspective.
I meant the map that induces the Siegel.
Oh, yeah. So these are induced by these row I maps that map everything to one element. So this is from n to 1, and it maps everything except for the ith entry to the fixed point. So it just deletes everything but the ith entry. So this one maps to 1 in this case, and the rest map to the star. Okay. Yeah, so a symmetric monoidal category is a Siegel op fibration over fin star. Okay. So I promise I did that for a reason. So we want to eventually understand what a G-monoidal infinity category is. Before I came up with that definition, in the literature, there was a separate definition for a symmetric monoidal infinity category. And it is basically just the infinification of this definition I've written down just now. So the existing definition was a symmetric monoidal infinity category is a co-Cartesian vibration is a Siegel co-Cartesian vibration over the nerve of finite pointed sets. Okay, so looking at this definition, it gives us a sort of strategy to how we might generalize this. So before I had the parenthesized symmetry operad, the action operad associated to the symmetric groups. And I generalized that to a given random PAG, which gave us a notion of a G-monoidal category. And so we want to come up with a sort of generic version of this nerve of finite pointed sets so that we can come up with a definition for a G-monoidal infinity category. And so what I'm going to do is I'm going to slowly build this action infinity operad, if you want, and then define G-monoidal infinity category to be precisely a Siegel co-Cartesian vibration over this thing. So to start with, I'm going to do this in quite a few steps. So to start with, I'm going to construct a two category, specifically a category enriched in groupoids. And I'm going to call this thing G groupoid. The objects of G groupoid are the same as the objects of the category of finite pointed sets. So they're going to look something like this. And then the Hom groupoids are going to be defined somewhat specifically. So from N to M is going to be defined as a coproduct over maps F in the Hom set N to M in the category of finite pointed sets. And then we're going to do a product over 1 less than or equal to I less than or equal to M. And then this is going to be op G F inverse of I. Okay, so what is op G? Op G is the same thing as PAG, but we got rid of the parentheses. So in this case, what does a given element of this Hom groupoid or object of this Hom groupoid look like? So it would need to have an underlying map of finite pointed sets. So maybe something as simple as this. Okay. And then we're going to need an element of, in this case, op G2, corresponding to the cardinality of the pre-image of 1, and an element of op G1, corresponding to the cardinality of the pre-image of 2 under this map F. So this is F. Okay, so we'd have just some sort of A in op G2 and B in op G1. Okay.
So what is op G?
It is PAG, the parenthesized action operad, where I got rid of the parentheses on the objects in the groupoids. So it looks something like, no more parentheses, but so like op B for the braid group would look something like this. Like that's a morphism in op B4.
So so when you look at F inverse of I, it's always just you're just looking at it as a set with a certain amount of elements. You're just looking at the cardinality.
I'm just looking at the cardinality. There should be lines there. Thank you.
So this Hom thing is itself a groupoid, but
yes,
the objects are always the same for any G, but
yes.
the morphisms is where the group comes in.
Mm-hmm. So it's sort of a generalization of the category of finite finite sets. So I want the objects to be the same, but I want to carry a bit more two-dimensional information that allows me to define more than one commutativity isomorphism. Not necessarily more than one, but it gives me the ability to do that. And just because of the way op vibrations work, I can't really do this unless there's two-dimensional information. But yeah, anyways, so
and A and B, I can just think of them as they're just permutations. Like A is just a permutation of 1 and 2.
yeah. So A could be like x2, x1, and then this would just be like x1. And then the 2 arrow in this groupoid would be given by some two different, if I had like another set of objects, it would be given by a braid on 2 strands and then just the braid on 1. Okay. Yeah, great. Okay, so far we just have a category enriched in groupoids, but I want to do infinity category theory, right? So before with the definition for a symmetric monodal infinity category, we took the nerve of the category of finite pointed sets. I'm going to do the same sort of strategy here, but I now have a 2 category, right? So what I'm going to do is I'm going to take something called the Duskin nerve, and I'll explain a bit about that in a second, of G groupoid. So Duskin nerve of G groupoid. And I'm going to call this G infinity. And this is going to be my action infinity operad. Now, if you haven't seen the Duskin nerve before, it works particularly nicely in this case because this is a category enriched in groupoids. So one way we could think about it is you look at all the Hom groupoids individually, and you take the nerve of those. This will give us a simplicial category, because now the Hom sets are actually Hom simplicial sets. And specifically, it's going to give us a category enriched in Kohn complexes, because the nerve of a groupoid is a Kohn complex. And then if I take the homotopy coherent nerve of that category enriched in Kohn complexes, it's going to give me a quasi-category, specifically, because it's enriched in Kohn complexes. So G infinity is a quasi-category.
Sorry, can I ask again a question about the definition
Yeah.
of the because you said this is supposed to generalize the category of finite pointed sets.
Mhm.
And I guess that would be the case where G is the symmetric group, but in that case,
Yeah.
there's still more information because you're not just having a map, you attach permutations.
This is true. It is. It does give a different definition. It's going to be isomorphic, though, because all of these Hom groupoids are completely contractible.
Or equivalent, but
yeah.
Okay, I see.
Sorry, equivalent, not isomorphic. Yeah, good question. Yeah. Anyways, okay, so cool. So we have this G infinity. And I'm going to play that same game I played before to explain the definition of a symmetric monodal category as an op vibration. So the first thing I'm going to do is I'm going to consider infinity functors or maps of simplicial sets between G infinity and the infinity 1 category of infinity 1 categories. So if I take, say, n here, I'm going to require that this is Siegel in the same sense. If I take n here, like this, a map from n to n, I'm going to have its underlying map of finite pointed sets be bijection, so that this is just like a permutation. So this would, I'm going to call sigma, and it corresponds to some specific swapping, some specific permutation on n elements. I'm going to call this map mu. and this map mu, and that's specifically the map, the underlying map of finite point sets that sends 1 through n all to 1. And then I have to pick an element in the pre-image of this, and it's just going to be the sort of like standard element x1, x2, ... xn, like this. Technically I have to pick n elements for this map, since there's n things mapping to n things. I'm just going to pick what the unit element in the first arity of this thing. So we can just think of this as id times n. And then that bottom mu is the same map. Now, because of the way the Duskin nerve was defined, if I have a element of, if I have an element G in PAGN, where pi n of G is equal to sigma, then I have something like this. And if I look at the image of this in the infinity 1 category of infinity 1 categories, I get out that same thing I was looking for before, where I have C of n, which is equivalent to C of 1, where that's just the Cartesian product of simplicial sets, over here to itself, down to C of 1, over mu, and this nice 2 simplex corresponding to sigma. So so it looks like it's giving me what I want, this sort of infinity functor or map of simplicial sets. But once again, I'm going to repackage this. So I'm going to use what's called the infinity 1 Grothendieck construction.
Is it really sigma, or would it be the element G?
Yeah. Sorry. Yes, absolutely. G. Thank you. G maps to sigma because it has to corroborate with the underlying permutation. But yes, this is associated to G, and that is what we want. Thank you.
You actually get one of these 2 cells for every G that induces the given permutation.
Yeah, exactly. Which is like exactly what we want in this situation.
Oh, it's like the different braidings, for example.
Yeah, exactly. Or like cactus group elements or ribbon braids or whatever. We want in the 1-dimensional case, we wanted a commutativity isomorphism corresponding to each of these group elements. That's telling me that I have this group action on the iterated monoidal product. Now, because we're in infinity land, we want a 2-cell corresponding to each of these things in this category, in this infinity 1 category of infinity 1 categories.
Oh, yeah, actually, that's what I want to clarify. So this diagram lives in cat infinity, right? C of brackets n is an infinity category. So I can think of that as an honest 2 simplex in the infinity category cat infinity. That is what it is. Okay, thank you.
Exactly. Yeah, awesome.
But is it correct that even if you want, like, if you wanted to do even like a braided monoidal category in the same way, you would need to consider 2 cells? Like if you just wanted an actual braided ordinary category, braided monoidal category, you would still need these 2 cells?
Yeah, it would be in the category of categories, though, which is how you can. So I only showed this op vibration definition for the 1 category case for symmetric stuff. But if you take, and this is where it gets kind of complicated. If you take the G groupoid corresponding to braids, so braid groupoid, and you take a certain 3 functor to the category of 2 categories, then you can get out what you're looking for. But you can also repackage that slightly so it's a little less confusing and you don't have to deal with a 3 functor. So you can do it with a pseudo functor but then it has to have these certain properties. So on the other side of things, instead of asking for an op fibration of categories, what you ask for is something called a discrete 2-op fibration of 2 categories. And so that would go from CO times or whatever down to braid groupoid, which is a 2 category now.
Braid group would be the replacement for the nerve of finite pointed sets?
Not the nerve. It would be the replacement of just finite pointed sets. So let me finish writing this infinity one Groton deconstruction stuff, and then I'll show you what the 2-dimensional analog is. So the infinity one Groton deconstruction allows me to repackage this information precisely as the way the definition of symmetric monoidal infinity category worked. And so I can say a G-monoidal infinity category is a Siegel co-Cartesian fibration over G infinity. Okay. But for braids in the one-dimensional case, a braided monoidal category can be defined as a discrete 2-op fibration CO times down to braid groupoid. And this is a Siegel one. Yeah. So I end up using this sort of view of G-monoidal 1 categories in order to prove a nerve theorem. So you can show that this is an equivalent definition for a G-monoidal category. There's a 1-to-1 correspondence with the algebra definition. And then the nerve of this discrete 2-op fibration is a co-Cartesian fibration, just because it's the nerve of an op fibration. And in particular, because the original one was Siegel, this one will also be Siegel. And so you get that the nerve of something like this is precisely my definition of a G-monoidal infinity category. Yeah, okay. So we have this definition now, and we're almost out of time, but I'm going to briefly write down some theorems that'll give you a good idea of why this is the right definition. This definition recovers all existing definitions of commutative monoidal infinity categories. And that includes symmetric monoidal up to equivalence. So this is all up to equivalence.
So it's a theorem that depends on the date for its validity. So up to the point of writing.
Yes.
Right.
It recovers the definition of symmetric monoidal infinity. It recovers the definition of monoidal infinity when you use the trivial action operand. And it recovers the definition of a braided monoidal infinity category, which is usually defined using little disk operand. And the reason why is because given a specific choice of base points, the fundamental groupoids of the spaces of the little 2-disk operand are the braid groups. And specifically, they give you PAG. So the next theorem is that nerve theorem I was talking about, which is that the nerve of a G-monoidal 1 category is a G-monoidal infinity category. So one important thing to note is that not only does this definition recover the existing definitions, it now supplies us with ones that we didn't have before. So we didn't have a definition, for example, a coboundary infinity category or a ribbon braid monoidal infinity category. And now we do. And there's a way to do this for any G-monoidal category now. And then we're basically out of time, but just as a last note, if you're familiar with Lurie's definition for an infinity operad, he essentially takes this existing definition of a symmetric monoidal infinity category, and he weakens it quite a bit. And so instead of requiring it to be a co-Cartesian fibration, he essentially says it has to be co-Cartesian over inert morphisms. And there are a few other requirements. If you play that same game with my definition, where you weaken the co-Cartesian part of the definition to be co-Cartesian over inert morphisms, yada, 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 then you get out a notion of a G infinity opera. And this also recovers all existing definitions, and it also has a corresponding nerve theorem. There is one other definition of a G monoidal or a G infinity opera that Donald Yao came up with, and it's using dendroidal sets, specifically G dendroidal sets, which come from G trees, like G labeled trees. And as a future project, I'm working on showing that there's like equivalent equivalence between model structures on these two definitions for G infinity operad. And yeah, so questions. I think people are messaging in chat. Okay. Cool.
I have a question, actually. Just about, so the definition of one of these things is it's a fibration over this G infinity, which is constructed from a group, I guess.
It's constructed from an action operad specifically. But yeah, it's constructed from like a sequence of groups that have like homomorphisms down to the symmetric group.
And I was just wondering if it makes sense to also, if there's like more general version that doesn't come from like groups, but something kind of a higher categorical version.
Oh, I hadn't thought about that. Yeah, I mean, certainly there should be. I'm not sure if like a blank monoidal category or like a maybe not use G, an H monoidal infinity category. I'm not sure how where that would appear naturally, where H is like some other infinity category. But yeah, that's interesting to think about. I don't know.
Or I guess another way of saying my question is, I was just like, what is the properties of these G infinities that make them suitable?
I kind of brushed over the definition of an action operad, but it's kind of what's required on a given action operad G is that it just makes sense to talk about a G monoidal category in a sense. Like you need this action on the iterated monoidal product, and you need it to be able to plug into itself in a way that makes sense, so that you can keep multiplying these things and then keep talking about the actions so that they're like coherent. Does that make sense?
Yeah, I think so. Yeah,
so at least the way I interpreted your question, like that sort of action operad, it doesn't have any like requirements on some like higher coherency information, like maybe some weird two cells connecting things or whatever. And I'm sure that you could generalize this further in some sense, so that you could have things that don't correspond to some sort of one-dimensional analog. But I have not done that.
Yeah, I have a related question, going back to Francis's comment. So in the symmetric monoidal infinity category case, those live over the nerve of finite pointed sets.
Yes.
There are certain nice co-Cartesian fibrations. And in the more general case with G infinity, now G infinity is not the nerve of a one category anymore, but it is the Duskin nerve of a track category, right?
Of a two category.
Yeah, but wasn't it groupoid enriched?
Yes.
Yeah, okay. I call those track categories because I guess I'm old-fashioned.
Oh,
And
okay.
so that's pretty close to a one category still.
Yes.
Right. So those are the kinds of infinity categories you'll see downstairs in that vibration picture.
Yes.
Right. Was there a reason a priori to not expect anything beyond two categorical structure? Or I guess maybe that's rephrasing Francis's question that
I think
you
it
might
is
have
just
a whole space, a whole infinity category to begin with.
I mean, there is no reason to expect that there shouldn't be. I guess the answer to the question is my goal with this project was to expand the definitions of what we know for like monoidal infinity categories. And the ones that existed were symmetric and braided.
Right.
And so
No,
using
this
this
is
sort of
great.
paradigm,
I love this.
so using this sort of paradigm of action operands, I could expand it further in that way. But yeah, I think there definitely is like a pattern there where if I were to pick something more elaborate, it should still work.
Okay.
But I don't know what requirements you would have to have on something
Right.
higher than
Right.
like a regular action operand.
I see. And I'm not very familiar with the Duskin nerve. I've heard the words, and the explanation you gave is perfectly fine. Just take the nerve of each mapping groupoid that's now category enriched in Kohn complexes, and you take the homotopy coherent nerve. I was wondering, very naively, looking at a groupoid enriched category, well, can I instead look at the groupoid enriched nerve? That's now a simplicial groupoid, having the original objects and then the let's see, morphisms and then morphisms cross morphisms over objects and all that. So you get a big simplicial groupoid, I guess. And then I'd be tempted to do something with that. Could you maybe take nerves degree-wise, view that as a bisimplicial set, and do something with that? So are there other ways of constructing the Duskin nerve? I'm not very familiar with the construction. Or do we have to go through the homotopy coherent nerve? As much as I love the homotopy coherent nerve, I was wondering if there's a more direct way of computing that infinity category downstairs.
I mean, so like short answer, I don't know. Long answer, I originally came up with this plan where I was just like, I'm gonna take the nerve of the groupoids and then take the homotopy coherent nerve. I later found out that that's equivalent to the Duskin nerve.
Okay. So that if I look up Duskin nerve in a book, that there's a difference, but
there is a different
definition
because it's I mean, a category enriching groupoids is a particularly nice two category, and the Duskin nerve works for two categories.
Okay.
So it is defined differently. It corresponds to that in this case.
I see.
Yeah.
Okay.
And so I mean, for me, it was like the only thing I cared about was this specific case where I have a category enriching groupoids, and so I'm not sure if it would be the same as doing first the simplicial groupoid or whatever.
Yeah, okay. I'll have to look into the Duskin nerve, but I mean, the description you gave is exactly what should be happening homotopically, so it's fine.
Yeah. I mean, that's why I ended up choosing that way. I was like, this is clearly what I want to happen. So.
Right. Okay, thank you.
Cool, yeah. Any other questions?
If not, let's thank Olivia for the very interesting talk.
Yeah, thank you. Thank you so much for having me. It's been fun.
Thank you. That was great.